This work is about the near-optimal algorithm for constructing greedy consensus tree. Here, near-optimal means optimal up to polylogarithmic factors. We first start with some background on phylogenetic trees. A phylogenetic tree is a tree structure in biology to represent evolutionary relations. There are two kinds of nodes in a tree, leaves and non-leaf nodes. Non-leaf nodes are also called inner nodes. So the leaves of the tree represents the species. For example, here, these three bears, they are the leaves of the tree. Each inner node of the tree represents the least common ancestor of all the leaves within its subtree. So, for example, here, the black bear and the white bear they share a common ancestor, but they do not share it with the teddy bears. Teddy bear is not a descendant of this common ancestor. Phylogenetic trees can be large. For example, this is the phylogenetic tree of the coronavirus, COVID-19. Leaves of the tree are the samples taken. Different colors represent different countries. Due to the inaccuracy of biological data and inference methods, different data sources may result in different phylogenetic trees. They may conflict with each other. We view each phylogenetic tree as a data point. If it is numerical data, we can take the mean of data points as a very good estimator. But here, the data we have are different trees. So consensus tree methods were proposed to summarize these different structures into a single consensus tree. The input of the consensus method is k conflicting phylogenetic trees over the same set of n species. Namely, each phylogenetic tree in the input has n leaves labeled from 1 to n, which are the n species. So our input size is of order kn. Many reasonable consensus tree methods were proposed based on different heuristics. The desirable running time of them is kn, which matches the input size. As we can see, many consensus tree methods did achieve this goal up to polylogarithmic factors, but one exception is the greedy consensus tree. Recall the input of the greedy consensus tree is k conflicting phylogenetic trees over the same set of n species, and the output is a single phylogenetic tree as the consensus tree. On these phylogenetic trees, we first define the concept of a cluster. A cluster LV is defined as the set of all the leaves within the subtree of an inner node V. For example, in this phylogenetic tree, different leaves are marked with different colors. And these leaves marked by the red color, these leaves form the cluster of the inner node V here. So this is a cluster. Since we have k phylogenetic trees, a cluster may appear in several different input phylogenetic trees. For example, here, the cluster ABCD is a trivial cluster. It appears in every phylogenetic trees as the cluster of the root. Then it's the cluster ABC. It appears in the first tree and the second tree, but it does not appear in the third tree because AB and C, they are separated. And the cluster AB appears in the second tree and the third tree, but not in the first tree because the first tree, the cluster of the inner node is ABC, not AB. And finally, CD only appears in the last phylogenetic tree, so it only appears once. When we have two clusters, they are consistent if only if they are disjoint or one of them contains the other. For example, here, the cluster ABCD is consistent with the cluster CD because ABCD contains CD. So what does consistency really means? Consistency means these two clusters, they can simultaneously occur in a single valid phylogenetic tree. For example, here, ABCD and CD can simultaneously occur in this valid phylogenetic tree. If we move the cluster CD to cluster DE, then these two clusters, they are not disjoint and no one contains the other one. In this case, these two clusters are not consistent. We can either build a phylogenetic tree that contains cluster ABCD, like this phylogenetic tree, or we can build a we can build a phylogenetic tree that contains cluster DE, but we cannot build a single phylogenetic tree which simultaneously contains the cluster ABCD and the cluster DE. So they are not consistent. As its name suggests, a greedy consensus tree is defined as the output of a greedy algorithm. The first step is to count the frequency of each cluster within the input trees, namely how many input phylogenetic tree contains the given cluster. We have done that before here. And the second step is to sort these clusters according to their frequency, from high frequency to low frequency. Ties are broken arbitrarily here. So ABC and AB, they appear with same frequency, namely twice. They can be sorted in arbitrary order. So we could have more than one valid greedy consensus tree from a single input, but that's okay. Then, from high frequency to low frequency, we try to insert each cluster into our consensus tree one by one. So among these clusters, the first cluster is our trivial cluster, ABCD. So we just put it here. And the second cluster is the cluster ABC. It's contained in ABCD as a subset. So we just insert it here, insert a new node, and make ABC children of it. The third cluster, AB, is containing ABC and ABCD, so it's consistent with every previous clusters. So we insert a new node here and make A and B children of it. The last cluster, CD, is not consistent with previous cluster, ABC, because they are not disjoint and ABC do not contain CD. So we just throw CD away. That's how this greedy algorithm works. It throws low frequency clusters away and keep the higher frequency clusters. In order to check whether a cluster is consistent with every previous inserted clusters, the naive implementation would need k times n cubic time, and it was improved to k times n squared time by Jensen and others. And then it was further improved to k times n to the 1.5 time complexity by Gavrilovsky and others. And there's also another algorithm which takes k squared n time by Song, which has a very different idea. And in this work, we improve the time complexity to kn times some polylogarithmic factors. So this algorithm is optimal up to polylogarithmic factors since it matches the input size. And our algorithm mainly adopts the ideas from this previous algorithm. So recall that the construction of greedy consensus tree contains two steps. The first step is to count the frequency of each cluster and sort them according to their frequency. The second step is to insert each cluster into the consensus tree if the cluster is consistent with our consensus tree. So the first step is relatively easy. To count the frequency of each cluster, you just need to distinguish different clusters, identify distinct clusters. To do so, if we allow randomization, you can use hashing to distinguish different clusters. And if we do not allow randomization, you can still use some bit string techniques to handle it. So this part is very easy. The hard part is actually to determine whether each cluster is consistent or not. This is the bottleneck of previous algorithm. In the previous algorithm, in order to speed up this consistency checking step, they use a smart idea, which is a characterization of consistency. Like if you want to check whether the new cluster is consistent with previous clusters, you will need to enumerate previous clusters if you implement it naively. But in their algorithm, they fully utilize the tree structure of our consensus tree, which allows them to avoid such enumeration. The idea works like following. This is our consensus tree, and this is the cluster we want to check whether it is consistent with our consensus tree or not. First, we mark all the leaves of the consensus tree that appears in the new cluster, cluster C. Then let V be the least common ancestor of all these leaves, namely V is the LCA of cluster C on the consensus tree. Then let W denote a child of V. The LW is just the cluster in the subtree of W. We have the following fact. The cluster C is consistent with our consensus tree if and only if it is the union of several such LWs. Like, for example, here, C is consistent with our consensus tree because it is exactly the union of these three LWs. This is a sufficient condition because we can insert our new node corresponding to the cluster C to be the parent of these Ws, whose cluster is a subset of C. This condition is also necessary because by the property of LCA, C must be a subset of this LV because V is the LCA of all the leaves in C. If C is not the union of several such LW, then there must be a set W that intersect with C but not contained in C. Then C conflict with this LW. Then C cannot be consistent with our consensus tree. So this proves the necessity of this characterization. In this characterization, we need to first find the node V, namely the LCA. We have k input phylogenetic trees, each with order n clusters, so we have order kn clusters in total. To implement this characterization, we need to maintain the LCAs on our consensus tree of all these clusters. We also need to add, sometimes we also need to add a new node to our consensus tree if the cluster is consistent. In this case, the consensus tree is dynamically changing, and answering such LCA queries will be a daunting job. This is the main difficulty of the previous algorithm, namely to maintain the LCA of kn static sets on a dynamically changing tree. It's very hard because if we add a new node to the consensus tree, the answer of many clusters in the input trees may change simultaneously. The previous algorithm spent a lot of effort into this. In order to overcome this difficulty, we choose to get around it. If maintaining the LCA of static set on a dynamic tree is hard, then what about maintaining the LCA of dynamic sets on static trees? That sounds much easier. Since if a set changes, it only changes its own answer. It will not affect the LCA of other dynamic sets. Namely, we conversely maintain the LCA of all clusters in the dynamically changing consensus tree on those k input trees. For example, for this cluster here, we maintain its LCA on each of the input phylogenetic tree. And this is the motivation of our algorithm. This is the previous characterization. To implement it, one has to first find the LCA, which is node V here. This becomes the main difficulty. To get around it, we need to modify the definition of V in our characterization. Intuitively speaking, if the new cluster C is consistent with our consensus tree, we're going to add it to be a child of V, and then some children of V will be children of the new node. So C should be a subset of LV. And so therefore, conversely, LV shouldn't be a subset of C. And if we pick an arbitrary leaf x0 in C, x0 has to be a dissident of the new node and the node V. So V should be the deepest ancestor of x0 such that LV is not a subset of C. This is the intuition behind our modification. So let V now be the deepest ancestor of a leaf, x0 in C, such that LV is not a subset of C. So if the cluster is consistent with our consensus tree, the node V defining this way actually coincides with the LCA. For example, in this figure, we first pick a leaf node X0, which is the node marked in red. The cluster of its first ancestor is a subset of C, so it does not satisfy its requirement. But the cluster of its second ancestor is not a subset of C, because this leaf is not contained in C. So this is exactly node V. As we can see, it coincides with the LCA of C on the consensus tree. But when the cluster is not consistent, the node V may diverge arbitrarily far from LCA. For example, if a cluster C now contains these 3 nodes, it is no longer consistent with our consensus tree. If we pick this node as X0, the deepest such ancestor would be this node. And such V is obviously not the LCA of these 3 nodes on the consensus tree. To check whether LV is a subset of C, we need the following fact. Suppose C is the cluster which is from the input tree Ti, and it is the cluster of the inner node U on Ti. Then we find the least common ancestor of all the leaves in LV on Ti. Namely, these are the leaves within LV, and we mark them red in Ti and find their common ancestor, least common ancestor. And LV is a subset of C if and only if this common ancestor is within the subtree of U. Then LV is exactly this set and it's a subset of C. Therefore, as a result, to judge whether LV is a subset of C, we only have to find the least common ancestor of LV on the input tree, which is the static tree. This is exactly our approach before. Namely, we maintain the LCA of each cluster in the dynamically changing consensus tree on the static input tree. Suppose we know how to answer these LCA queries, then we know how to judge whether LV is a subset of C. Then, because if LV is not a subset of C, then all its ancestors, all the clusters of its ancestors cannot be a subset of C. Then we can just binary search the path from X0 to root to find the deepest such ancestor to be the node V. As a result, our modified characterization can be implemented by this LCA queries, where we maintain the LCA of each cluster in the dynamically changing consensus tree on those static input trees. Now we move on to discuss about how we can answer such LCA queries. Recall our idea is to maintain the LCA of dynamic sets on a static tree. Let us now forget about our consensus tree for a moment. If we have a static tree Ti and a dynamic set S of nodes on Ti, how can we support addition, deletion to the dynamic set S and at the same time maintain the LCA of all the nodes in S on the static tree Ti? This is actually a very simple task. We maintain S, the dynamic set, in a binary search tree in arbitrary order. Each node on the binary search tree corresponds to a node in S, which is also a node in the static tree. At each node, we store the LCA of all the nodes within subtree. Namely, for example, for this node in BST, it corresponds to the node E in set S and the static tree. And we store the LCA of all the nodes within its subtree in BST at this node, namely the LCA of A, B, C, D, and E. Note we do not have to recompute this LCA from scratch. We can compute this LCA from the LCAs stored at its children. Namely, this is just the LCA of LCA ABC and LCA D and the node E. Because it's a binary search tree, sometimes to keep it balanced, we may have some rotation operations. When we have a rotation, for example, like this, for each rotation, a constant number of nodes change their children. In this case, we need to recompute the LCA stored at that node from those two LCAs stored at its children. This needs only a constant number of LCA queries on TI, which takes constant time. Now we move on to introduce the data structure we used to maintain the LCA of every cluster in the consensus tree. We now describe the structure only for the case where there's only one such phylogenetic tree in the input. Since there are actually k such phylogenetic trees, we simply replicate this data structure k times. First, since we need to insert new nodes to our consensus tree, we use an arbitrary dynamic tree structure like LCT or top tree to maintain our consensus tree. At each node of our consensus tree, we store the LCA of its cluster. As before, we do not have to compute this LCA from scratch. It equals the LCA of the LCA stored at its children. For example, at this node, we maintain the LCA of its cluster, which is exactly the LCA of these two leaves, which is the red node. That's why this node is marked with red color. And for this node, we do not have to recompute its LCA from the LCA of these four leaves. We can just compute its LCA from the LCA of its three children. Since we have insertions, a node here may lose some of its children or may attain new children. Therefore, the set of its children is actually dynamic. Then we use the data structure we introduced in the last slide to maintain this dynamic set. Namely, for each node of the consensus tree, we maintain a BST inside it, which contains the LCAs stored at all its children. When we actually insert a new node, some children of its parent become children of it. So we need to move these children from the BST of its parent to its own BST. If most of the children remains at the parent, which is the case drawn here, we do so by delete each of those children which go to the new node from the BST and insert them to the new BST. But if most of the children go to the new node, which is the case drawn here, we delete the children that remains at the parent from the BST of the parent and directly give the BST to the new node. And then we rebuild the BST of the parent from scratch. Since finally the consensus tree contains at most n nodes, there can be at most n insertions into the consensus tree. Each time we split the set, we only enumerate the smaller part of the set. Therefore, we produce at most n log n insertions and deletions to our BSTs. And also remember that we replicated this structure k times for those k phylogenetic trees in the input. So in total, we have kn log n's these deletion and insertions to our BSTs. As a result, our algorithm works in O tilde kn time, which is near optimal. Thank you very much for listening.